Have you ever just looked up at the sign and thought about its incredible power? I mean, really thought about it. Well, what if I told you we could build a tiny version of that star right here on Earth? That is the absolutely mind-blowing goal of fusion energy. It's truly one of humanity's greatest scientific quests, and you know what? The finish line might be a lot closer than you think.
And hey, don't just take my word for it. This is the head of the International Atomic Energy Agency saying we are closer than ever to making this happen. That is a huge statement. It signals a real fundamental shift. What was once the quiet hum of a far-off research project is quickly turning into a roar of excitement.
Okay, so what does it actually take to build a star on our planet? It's a story of some truly monumental challenges for sure, but it's also a story of incredible breakthroughs that are happening as we speak.
So first, let's talk about the why, right? Why have we been chasing this seemingly impossible goal for decades? Well, it all comes down to the incredible, game-changing promise of what a star can do for us.
At its heart, the basic idea behind fusion is actually pretty elegant. We are literally just copying the process that powers the sun. You take light atoms, like different versions of hydrogen, you force them to combine, or fuse, and in that process they form a heavier atom and release an absolutely staggering amount of energy. And the vision this creates, well, this is why we call it the holy grail of energy. Unlike traditional nuclear fission, there's no risk of a chain reaction that could spiral out of control. A meltdown is physically impossible. The fuel, we can get it from seawater, and the waste, it doesn't create the kind of long-lived radioactive stuff we worry about today. We're talking about a clean, secure, and nearly limitless energy source. It's what we've been dreaming of.
So if the payoff is that incredible, what's the catch? Why isn't fusion power already lighting up our cities? Well, because trying to bottle up the power of a star here on Earth is one of the hardest things humanity has ever attempted. For decades, all the progress has been about tackling 5 absolutely immense challenges. Yeah. It really boils down to these 5 huge hurdles. You have to create unimaginable heat, you have to contain it somehow, find materials that won't just vaporize, create your own fuel as you go, and then you have to actually turn all that cosmic power into usable electricity. Let's break them down. First up, the heat. To get atoms to fuse, we need to get them to temperatures over 100 million degrees Celsius. Let that sink in. That is more than 6 times hotter than the very center of the sun itself. Just insane. So how in the world do you contain something that's 6 times hotter than the sun? Obviously, no physical container is going to work. It would just vanish instantly. The solution is just pure genius. Scientists use incredibly powerful magnetic fields to create what they call a magnetic bottle. This invisible cage, often inside a donut-shaped reactor called a tokamak, actually levitates the superhot gas, the plasma, keeping it from touching anything at all.
But even with that amazing magnetic shield, the walls of the reactor are still in a total war zone. They're getting hammered by stray heat in just a fire hose of high-energy particles called neutrons. This has created a massive material science problem. How do you find a material that can survive that kind of cosmic assault for years and years?
And then you've got the fuel itself. One of the key ingredients, an isotope of hydrogen called tritium, is incredibly rare here on Earth. So the solution is just mind-bending. The reactor has to make its own fuel. The plan is to line the reactor with a blanket made of lithium. When those neutrons we just talked about fly out from the fusion reaction and hit that lithium, they create more tritium fuel. This self-sustaining fuel cycle is an absolute, no kidding, make-or-break part of the whole concept.
Now, for decades, those challenges seemed almost impossible. Fusion was always the energy source that was 30 years away, but something's changed. Right now, at this very moment, we are seeing an unprecedented surge of momentum.
You want to know the biggest sign of this new era? Just follow the money. Over $6 billion in private investment has flooded into dozens of fusion startups. This isn't just a government science fair project anymore. Serious, savvy investors are betting big that fusion is on the verge of becoming a real commercial technology. And that bet is being backed up by some truly historic breakthroughs. At the U.S. National Ignition Facility, scientists hit a milestone for the ages. They achieved ignition. For the first time in history, a fusion reaction produced more energy than the laser energy that was put in to start it. This was the Wright brothers' moment for fusion, the absolute proof that it could be done. And that was just the spark. The team at NIF beat its own record just a few months later. At the same time, teams in China are setting new records for how long they can keep that plasma stable. And in Germany, this wild-looking machine called a stellarator,
which is a totally different take on the magnetic bottle, is also hitting new performance highs. The pace of innovation is global and it is accelerating fast.
All this progress is fueling a global race. And it's not just a race for scientific papers anymore. It's a race to build the first generation of actual fusion power plants, what are known as demos. And this has kicked off a serious international competition. You have major projects popping up everywhere, from China and the EU working on more conventional designs, to the UK developing a more compact, spherical version. It's a crystal clear signal that the whole world is committed to getting fusion onto the grid. Now, at the heart of this huge global effort is ITER, located in France. It is one of the most ambitious science projects in human history, a massive collaboration between nations to build an experimental reactor that will pave the way for all these future demo plants. But even as the science rockets forward, building a true fusion-powered future means we have to look beyond the lab. Now we're facing a whole new set of practical, real-world challenges.
And one of the first things on that list is regulation. Now, this is really critical to understand. Fusion is not fission. The physics, the risks, the safety profile, it's all completely different. And this is so fundamental that countries are literally writing entirely new rulebooks. The UK, for example, is planning to regulate fusion plants for their environmental impact, not as traditional nuclear sites. That's a huge, huge distinction.
And the list just goes on from there. We need to build an entire global supply chain for these highly specialized parts. We need to develop advanced robots that can do maintenance inside the reactors. We need to train a whole new generation of scientists and engineers. And we have to write the legal frameworks for this brand new industry.
But that same spirit of collaboration that got this whole journey started is still going strong. As the head of the ITER project puts it, the goal is to work together, to channel all this incredible effort into a shared solution for all of our futures.
Which brings us to the final, critical question, doesn't it? The physics problems are being solved. The engineering is moving faster than ever. The investment is pouring in. So maybe, just maybe, the final hurdle isn't technical at all. Maybe it's about us, our global will, our policies, and our collective commitment to finally finish this race and bring the power of a star down to Earth.